So we've been talking about the irreversible nucleophilic addition reaction, and the first reaction we came across was the reduction of ketones and aldehydes with hydride equivalents, things like sodium borohydride and lithium aluminum hydride. Now let's take a moment to think about the transition state for this transformation. So consider the reduction of the following ketone. And so if we have a ketone like this that has let's say a terp-butyl group at this position. The reduction products here would be slightly different. So we have to draw this ketone in its sort of pseudo-chair conformation. And that's because we want to have that terp-butyl group sitting up. We want to have it sitting up because it's going to be in an equatorial sense. And so we have two different modes of attack here. All right, so if we were to react this with LAH, right, and we'll consider the mode of attack here A, so the sigma aluminum hydride bond, which is our nucleophile. Let's say that A attacks from the top face, right, the top lobe of that pi star CO orbital. And let's say we have another mode of attack with the same reagent, LAH. Let's say that this is mode of attack B with another sigma aluminum hydride bond. And this attacks from the sort of bottom face, a bottom lobe of that pi star CO. All right, so we've got the pi star CO kind of sitting right here and here, right? And we're going to attack via one of those two lobes on the carbon atom, right? Because that's where the biggest electron sink is. Okay, so from this most stable conformation, we're going to get actually two different products. The first product we're going to get by mode of attack A is going to have the terp-butyl group and the alcohol group after protonation in a trans fashion. Okay. The next mode of attack is the mode of attack where you've got the terp-butyl group and the alcohol group in a cis fashion. Right? And so this is going to look like terp-butyl is sitting on the opposite side of the alcohol, and this is going to look like the terp-butyl group is sitting on the same side as the alcohol. All right, so these different modes of attack, these different faces make the transition states diastereomeric. Right? We get two different diastereomers because indeed the products themselves are diastereomers. Right? So in this LAH reduction, we're going to get more of the trans product than we are going to get more of the cis product. All right, so let's take a look at what that might look like from a reaction coordinate diagram sense. Going to lead us to the trans product to label A. So I label that with okay. So let's say that we've got this this ketone in the middle. All right, this ketone in the middle has some energy. Let's say right there, and let's say we're going to react it so that we get the cis product. So mode A. Right. So that cis product, mode A. So we know that the trans product is going to be much more stable, right, than the cis product. So let's draw out the energy levels of those two products. So there's the trans product, and here's the cis product. Let's say that's slightly higher in energy than the trans product. Okay, so if we're connecting those two, we know that there's an energy difference, an energy gap between those two molecules. Okay, and this energy gap we say is the delta G of the reaction, the difference between the energies of those two. Okay, so this says nothing, although, about the energy of the transition states. So the mode of attack A versus the mode of attack B is controlled by the energy in the transition state. So let's draw out the mode of attack for A. So the mode of attack for A is going to be, let's say, this one. And so we'll call it transition state 1. Right, so this is the mode of attack A in blue. All right, so the mode of attack A is right here. And so this mode of attack is what we call an axial attack. Okay, so the hydride is coming from the axial position. The mode of attack B is going to also occur, but it's going to be higher in energy than the mode of attack A. So we'll call this transition state 2. And I label a green set of arrows. And so the mode of attack B is what we call equatorial attack. Okay, and the equatorial attack would have to come from this face, and what would have to happen is as you approach that face of the molecule, you have to basically bisect those two hydrogens, and so there's some steric strain there that is occurring. And so this transition state is slightly higher in energy. Okay, so we now have two different transition states, and we can, of course, attempt to consider the difference between these two transition states. So this is the delta G double dagger, and this is the energy of the energy difference between the two transition states. All right, so we've got the delta G double dagger 1. We've got the delta G double dagger 2. And then the delta G is just the difference between those two. Of course, if we go on the other side, the energy difference between the starter material and the product, that's the delta G, let's call that A. And then on the other side, this energy difference is delta G B, where the difference in energy between those two is the delta G. Okay, and so let's take a step back here. So what we're saying is that the mode of attack that's the axial attack, A, is lower in energy than the mode of attack B, which is the equatorial attack. And we can justify this because of the two hydrogens that are sitting in an axial sense that are kind of blocking the approach to the equatorial attack. So A is a lower hill to climb over, and so it's going to funnel into the product here. And so what happens is that we get mostly the trans product. But what would happen if this reaction were reversible? If this reaction were reversible, what we could do is then we could go back up the hill from the trans product towards double dagger 1, back to the starter material, and then if we had enough energy, go back over transition state 2, double dagger 2, into the cis product. Right, so that's kind of the thing that we're trying to decide. So in the LAH reduction, the product distribution is in favor of the trans product. And this should indicate to us that the reaction gives the more stable species, right? And so you might think that this reaction is under thermodynamic control, right? That the reaction is reversible and you're always going to get the more stable product. Okay? We say that since the energies of the products have no effect on the product distribution, and then the energy of the transition state is what's controlling the reaction, this reaction is under kinetic control. Okay? And so irreversible nucleophilic additions are under kinetic control. So this means that they're controlled by the energy of the transition state. And so these reactions are not reversible. They're irreversible. So what makes this reaction irreversible? Well, look at the mechanism and see if each step itself is reversible. So in order for the reaction to be under thermodynamic control, the nucleophilic addition step must be reversible. Right, so this must mean that an H minus would have to be a leaving group. All right, so let's do the thought experiment. If we had a tetrahedral intermediate like this, and we wanted this reaction to go in the reverse direction, so we're asking ourselves that question, what would have to happen is you would have to take the electrons, move them down to form a double bond, and then H minus would have to be your leaving group. And so what we would get is the ketone back plus H minus as the leaving group. Now we know this can't happen, right? Because the pKAH of the hydride is 32. And so this step is under kinetic control. Basically, you can't go in the reverse direction. The second step, the protonation of the alkoxide, gives the product alcohol, and protonations are reversible since protons can tunnel. So this one is under thermodynamic control. But overall, the reaction is under kinetic control since that first step is irreversible. Okay, so besides hydrogen equivalents, there are other nucleophiles that can add to carbonyls irreversibly. And those are the Grignard reagents and the organolithium reagents. And they add to the pi star efficiently under kinetic control. These reactions are irreversible in the first step because the reverse reaction would require a carbon-based anion to be a good leaving group, and we know that carbon-based anions have a pKa of greater than 50. So nucleophilic additions can only be under thermodynamic control if the incoming nucleophile is also a good leaving group, right? A pK of less than 15. So the difference between the reductions of ketones and aldehydes with a hydride equivalent is that the addition of Grignards and organolithiums will give you a different product. So Grignards will give you the formation of a new carbon-carbon bond instead of a carbon-hydrogen bond. So let's say we take this Grignard reagent and we react it in the presence of this aldehyde. So the aldehyde is our starting material, and that aldehyde is electrophilic, right, because it's got a pi star CO that's fairly low. Okay, we're going to quench this reaction with ammonium chloride, and so the a product that we get from this reaction is going to be a new carbon-carbon bond to form in between the phenol and the carbon that was formerly the aldehyde, and that's going to give us a secondary alcohol. Okay, so Grignard reagents react with aldehydes to give you secondary alcohols. Likewise, organolithium reagents react with aldehydes to give you secondary alcohols. So let's take organolithium reagents and now let's react them with ketones. Right, and so instead of a Grignard reagent, let's now start with an organolithium. You could have started with a Grignard reagent as well, and you get the same result. Let's react this now with a ketone, and let's quench it, of course, again with ammonium chloride. This time we're starting with a ketone, so nucleophilic addition occurs to give you a product. This product is going to look like this, in which you now have a new carbon-carbon bond right here between the butyl lithium and the formerly carbonyl of the ketone. And so this is an example where an organolithium or Grignard reagent reacts with ketones to give you tertiary alcohols. So how does it work? Well, it's the same mechanism. It's nucleophilic addition to the carbonyl. And so let's take a look at how that might occur for the for the Grignard reagent. Okay, so for the Grignard reaction, we've got a phenyl magnesium bromide, which is generated by taking an aryl bromide and reacting it with magnesium metal. So now we have a carbon-magnesium bond, which is going to be our HOMO, and it's going to react with the benzaldehyde as our LUMO, right? So the pi star CO is our LUMO. And it's going to attack via that Berge-Dunitz trajectory, and it's going to give us a new carbon-carbon bond. And so the new carbon-carbon bond is going to form. Electrons are going to move up onto the oxygen atom as a lone pair, which then is going to bond to the magnesium. And so our new carbon-carbon bond is of course that one right there. Okay, and so this species is this tetrahedral intermediate. It's in brackets, and it's going to then become protonated by taking ammonium chloride and quenching the oxygen magnesium bond to give you the product secondary alcohol. Okay, in the case of the organolithium, it's the same thing. And so we're going to take our organolithium. This time the organolithium is going to be a sigma carbon lithium bond as our HOMO. We're going to react it with the ketone. This time the ketone is acetone. And so you've got a pi star CO is the LUMO. You're going to take the carbon-lithium bond, attack via that Berge-Dunitz trajectory to give you a tetrahedral intermediate. And so now you have an oxygen lithium bond. And our new carbon-carbon bond is that one right there. All right, this oxygen lithium bond is then going to be quenched, of course, by ammonium chloride. To give you your product, which is now a tertiary alcohol. And so we can apply this type of thinking to synthesis. So tertiary alcohols and secondary alcohols can be made in several different ways. And so let's take a look at the following alcohol. So let's say we have this alcohol here, and this alcohol can be made in different ways depending on which kind of bond you want to break. So we're kind of thinking about this now in terms of retrosynthesis. So let's say we made this tertiary alcohol by severing this bond here, this A bond. And so if we wanted to sever that A bond, we would have two different pieces. We would have the piece that would formerly be the organogrignard reagent or the organolithium reagent, and we'd have the piece that would be the ketone piece. So if we're severing that bond, we'd have one piece here, which is going to be our piece that doesn't contain the alcohol, and so that's going to be the Grignard piece, or the organolithium piece. And so let's say that one is the organolithium piece. And then we have the other piece here, which is going to be the ketone piece. And so we've got a phenyl and a terp-butyl group that are on opposite sides of a carbonyl. So let's just draw that in. So those two things could potentially react to give you that tertiary alcohol. let's say we want to start by severing this B piece instead. So with the B piece, we're going to have to separate this into some piece that has no alcohol, so this terp-butyl group, and so that, let's say, is going to be our Grignard piece. And then our piece that contains the alcohol, this one here, in which we've got a phenyl and a butyl chain that are on either side of a carbonyl. So you add those two pieces together, you get the same alcohol. And then finally, if we were to sever this piece by breaking, let's say, the A bond would have, again, two different pieces. We would have this piece here, which we can say is either the organophenolithium or the phenyl magnesium bromide. Let's just pick one. Let's say it's the phenolithium. And then we'd have a piece that contains the alcohol, this piece right here, which has a terp-butyl group and a butyl chain on either side of a ketone, carbonyl. And so you can see how you can devise three different ways of making the same tertiary alcohol by using some combination of ketones and organogrignard reagents. You can apply this same kind of thinking to secondary alcohols, in which you'll have two pathways will be forming carbon-carbon bonds by doing organogrignard or organolithium reagent additions to carbonyls, and one pathway in which you're doing a reduction using sodium borohydride or lithium aluminohydride.